Hi everyone, welcome to meeting number 22 of the M2D2 series. We are excited to have Joe with us today to discuss how to integrate structure-based and ligand-based modeling for drug design. Joe is a PhD candidate in Run Drug Group at Stanford. He has graduated from MIT with a degree in computer science and molecular biology in 2016. Thank you, Joe, for taking the time to share your work with us today. And without further ado, the floor is yours.
Great. Yeah, thanks so much. I really appreciate the opportunity to speak to you all today. I'm excited. And yeah, so as I'm going through, please feel free to ask any questions by using the raise hand feature, and I'll try to get to them. Maybe any kind of like longer like discussion, like interesting future work questions we can save to the end, but yeah, feel free otherwise to raise your hand and ask. So I think that at a high level, if we think about the methods that we use to model the interactions of small molecule drugs with a specific target protein, they can largely be broken down into two camps. So the first, and two camps basically based on the types of information about the target protein that they used. So the first would be structure-based methods, where here the primary source of information is going to be the structure of the target protein. And such methods will generally predict a binding pose for the ligand and also give an affinity prediction based on the sort of the physical interactions that could potentially form between the small molecule and the protein. And the alternative approach is of course, these ligand-based methods where we don't care about the structure at all. And instead, our source of information is simply sets of other ligands that we know can bind this receptor, or perhaps labeled affinity data. And so both of these methods sort of have their own advantages. For instance, structure-based methods promise to be able to give good predictions with little to no sort of known small molecules for the target. Whereas in cases where you have a lot of data, at least my feeling is that the ligand-based methods generally outperform the structure-based methods once you have enough data. So the kind of the impetus for our work was this question of, can you use both of these types of information together, sort of while retaining like a lot of the benefits of each of these methods? And so I'm going to talk about first a method for binding pose prediction. So predicting the 3D coordinates of the ligand in the binding site. And then towards the end, I'm going to talk about sort of an extension of this method to work for binding affinity prediction. So binding poses are generally predicted using physics-based docking. So basically, these methods will take the structure of the protein and the 2D graph of the ligand, and they'll sample a bunch of poses, and they'll score them based on the energetic interactions between the protein and the small molecule, and pick out what it thinks is the best one. However, unfortunately, the results are often incorrect. In our benchmarks, about half the time. So we wanted to ask, what if you just simply knew a handful of other ligands that can bind to the receptor? So here we're going to say, so in addition to knowing your target structure and your query ligand here, you also know that these other, I think there are eight other ligands can bind to the receptor with some reasonable affinity. And so yeah, so we developed this method, which we call combined, a bit of a pun, that works to make these predictions using all of this information together. So the question is sort of like at an intuitive level, like how could this work? Like how could you sort of transfer this fundamentally 2D information into predictions about a 3D structure? And so where we started off was with kind of this observation that if you have different compounds that bind to the same target, they'll often form similar interactions. And this might be kind of obviously true for kind of chemically similar compounds like these two on the left. But we noticed that chemists often assume that even for like very different ligands like this one, that even though it has a completely different chemical scaffold, it still is able to form these two key hydrogen bonds. So we wondered if we could somehow exploit this, I don't know what to call it. It's not really an effect because there's no real physical basis, but sort of just statistical tendency for the ligands to form similar interactions like this. I should briefly note that I think that the intuition for why it might be that the ligands will form similar interactions like this is that sort of specifically in the context of the protein, it might be that these interactions are particularly favorable. For instance, it might be hard for water to form this hydrogen bond in the absence of a ligand, so you get a particularly big energetic reward. So sort of all of the ligands that bind sort of forming this interaction. So yeah, we thought that we could come up with a method that sort of simultaneously optimizes for both being physically reasonable and similar interactions. So the idea is that, so say if we have our compound of interest, we're going to generate a bunch of candidate poses. And then if we have a bunch of additional known binders, we're going to generate a bunch of candidate poses for them too. And then we're going to pick out a set of poses, one for each ligand, such that every pose individually sort of has a decently like physically reasonable, like a decent docking score. And together they sort of form a self-consistent set. So they form similar interactions with each other. And so, yeah, so in terms of quantifying physically reasonable here, we'll get to this in more detail later, but basically we're just going to use physics-based docking scores. Like that's a great metric for whether a pose is physically reasonable. But sort of quantifying this similar interactions and what exactly this means took a bit more work. So there's sort of two things that are challenging. So the first is that when we're at test time, when we have our data for the target of interest, at least by the assumptions of our method, we don't know the binding poses for any of these ligands. So there's some sense in which we can't train a model per se, specifically on the data here, because we simply just don't know which poses are right for any of these ligands. Right. And the other problem is that even if we did know this information, we really wanted to focus on this regime where we have just a handful of known binders. So even if we did have these labels, it's sort of unlikely that we'd be able to train a model that would generalize well for the data that we have. So what we do is instead of training our model on the target of interest, instead we set up this data set, which is composed of pairs of cases where you have the same protein co-crystallized with two different ligands. So in total, well, we had a lot of pairs. In terms of just unique ligands and proteins, we had just shy of 500 ligands across 30 different target proteins. So yeah, this resulted in thousands of pairs like this. and the idea is that, so here we're gonna learn sort of about the structural similarity of these ligands, and then we're gonna transfer that knowledge to our target of interest. So, right. So using this training data, the way that we set up our model is we essentially learned like a naive Bayes type scoring function. So what we do is that for each of the ligands, we generate many candidate poses, and then for each pair of poses binding to the same receptor, we compute sort of a set of similarity metrics between the pairs of poses. And these are things that we hand defined. So for instance, we have a hydrogen bond similarity metric. So here we record the set of residues with which the ligand is forming hydrogen bonds. And then we ask for the pair of poses, to what extent does this set of residues overlap? So what you're seeing here is sort of a Tanimoto coefficient with some pseudo counts added to make it well defined when we had zero interactions. But right, so the idea is that then once we have all of these the similarity metrics for each pair of poses, then we write down aggregate distributions for sort of all of the correct docked poses, and we compare this to the distribution for just all of the docked poses. And yeah, to focus back on this hydrogen bond, what we observe is that when we look at the correct docked poses, they generally have a higher degree of similarity to each other than if you look at all of the docked poses. So what this is sort of telling us is that the ligands tend to form similar interactions sort of more often than is predicted by physics-based docking on its own. And yeah, so in terms of the similarity metrics, so we had three that were sort of capturing similarity of interactions, so either hydrogen bonds, salt bridges, or hydrophobic contacts. And then we had a substructure similarity term, which is, so this is only defined in cases where ligands share a chemically identical scaffold of 50% or more of the size of the ligands. And so here, then this is just the RMSD between the shared scaffold in the two poses. Yeah, and so then to kind of put everything together into what we'll call the combined score. So the combined score is, you're going to get as arguments a set of poses, and then we're going to have two terms. So this first term is just going to be the sum of their physics-based docking scores. And then the second term is going to be this kind of like naive Bayes type. You're looking at the log ratio of the frequency of observing this degree of interaction similarity or substructure similarity in correct poses versus in all poses. And of course, so this is in here, it's across in the distribution for our whole training set, not just the target of interest. Yeah, and yeah, it's the one last interesting thing that we added was this. We normalized this term in terms of the number of ligands that we have, and basically this is I think kind of from in like the formal sense, like we're assuming that basically the information that we get from all of the different helper ligands is sort of redundant. So if you had two, it's not like you're getting twice as much information. We're assuming that you're kind of getting the same amount of information. I suspect like the optimal would be some sort of like 1/square root of n or something, but we didn't want to try to fit too much because yeah.
I see that you don't include the ligand in the right side of the equation, like the second right side of the equation. So, and I wonder why.
Yeah. Sorry. So to be clear, this so this frequency of similarity in the correct poses. So, oh, actually, yeah. So one thing that's going on. So here, like the arguments here are going to be the ligand pairs, right? So it's going to be one of these similarities. So what's going to go on here when we're evaluating this term is, so say that the ligands have the similarity of 0.75 for one of the interaction types, then what we're going to plug in is the value here and here into this term and this term.
Okay, I see. Thank you.
Yeah, of course. Yeah. So yeah, so to move on to some results. So we applied this model to about 30 different proteins and trying to get a good score spread over different target classes. And we found that we consistently got sort of like reasonable improvements over docking. I think in about half the cases, there's no change, and in about half the cases, we see an improvement. So yeah, we were very encouraged by this. And yeah, interestingly, we found that there's only one target for which on average we did worse. So we thought it was nice that we got sort of either about the same or a decent bit better performance. And yeah, and what I thought was really cool and that we were able to get, I think, from this kind of transfer learning setup that we have. Yeah.
Coming back to the previous figure, was there anything particular about that particular target that make combined worse than the classical docking method?
Yeah. So this is a good question. I think that the one area that I think combines, yeah, there's a few. I think that some things that can make combined struggle is actually related to the relative simplicity of kind of how we're featureizing the interactions. So basically, that we're just sort of treating in terms of just like hydrogen bonds, hydrophobic contracts, and salt bridges. I think for some families, I think in particular GPCRs and ion channels, where you have a nice mix of hydrogen bonds and hydrophobic contacts, that this is mostly expressive enough. But I think other cases where there's either mostly hydrophobic contacts or mostly hydrogen bonds, it kind of ends up that you can move the ligand around quite a bit and it will still have about the same features in terms of how we have it in our model. So yeah, I think this is a big cause for the model performing better in some cases than others. I don't know if this is kind of fundamental or if it's something we could improve by improving our featureization, but yeah, that seems to be the big contributor. One final case is cases where there seems to be a lot of like important interactions, like with the solvent, because we don't have any sort of term that's capturing, like even if you're pointed out to the solvent, it might be that you want to put hydrophobic groups there, or like yeah, or hydrophilic groups, depending if there might be like lipid or water in that particular part of the solvent.
Okay, thank you. There's a few more questions in the chat. Don't know if you
Oh,
can read them.
great. Oh, great. Okay. Yep. So the baseline docking method that we're using is glide in SP mode. Using more or less default parameters, we increased the sampling bandwidth just so that way we could get more cases where there's at least one correct pose in the list. and we always considered up to 100 poses for each ligand. And yeah, so predicted correctly is defined as having a RMSD of under 2 angstroms. Jonathan?
Yeah. Hey, Joe. This is really cool stuff. I remember reading the paper when it came out. One thing that I'm very curious about is what about in terms of diversity of interactions? Because, obviously, if you got a crystal structure, it means somebody has explored this and developed drugs for this, or potentially, and there are interactions often that are in unexplored regions that you could find a new inhibitor for. But if you're sort of using what you already know, you may never find those. So was there a metric that you used to enforce diversity, or is this something that you've noticed, or anything about that?
Yeah, that's a good question. So one thing that we, just in terms of our benchmarking setup, that we did is that we required that all of the ligands that we include in our benchmark are chemically distinct from the structure that we're docking into, if that makes sense. So this doesn't quite get around the case of, it could be that some of your other helper ligands are sharing a similar scaffold, but it's at least showing like the system as a whole is sort of discovering new ligands from what you've co-crystallized. But yeah, that's a good question. So the second part of the talk is going to be on a virtual screening application. So there I did impose some like specific constraints on the helper ligands being different than the kind of the query ligands. So yeah, I think I'll answer your question there. Yeah.
Cool, thanks.
Yeah. Oh, right. Okay. And then there's a question in the chat about how the similarity of 3D poses is calculated. Yeah. So the idea is that we have sort of these 4 different metrics here. So the first 3 are quantifying whether the ligands are forming this type of interaction with the same set of protein residues. So they're asking, like, does the ligand form hydrogen bonds with the same specific residues? And the way we do this is for 2 binding poses, we record the interactions, and then we take like a Tanimoto coefficient between the two sets. Yeah. Okay. Sure. Yeah, I think that's, yeah, depending on how you define 3D. Yeah. So yeah, and so yeah, something that we we're excited about in the results is that we found that even with very small numbers of known binders, we were able to get a boost. So interestingly, even if we just had one known binder, we were able to get an appreciable increase in the fraction of ligands whose poses are predicted correctly. And one thing that I should mention is that, so when we were doing these benchmarks, so our query ligand, so the one that we're going to assess whether or not is correct and is going to kind of contribute to these benchmark numbers, of course we had a co-crystal structure for, but for the other known binders, we simply just downloaded other ligands from Chembl. So we picked for a given, so say like we're assessing for beta 2, we went to Chembl and we took the first 10 highest affinity ligands and used them as the helper ligands. Yeah, and so just quickly, we used our method to make some kind of prospective predictions for the binding poses of some antipsychotics at the D2 dopamine receptor. And yeah, I think this example is like illustrative of some way that the method can work. So I wanted to share it. So interestingly, we found that when we run docking, we get this pose for pimazide. And if we inform the prediction using some other ligands that share a common scaffold, we find that we get in exactly, more or less exactly flipped pose. So I think there's two questions that are of interest. The first is, why did Combine decide just to flip the poses? Or I should mention, the real question is, it's kind of by construction, the method is going to tend to put the ligands in similar poses. So it won't always, but will tend to form either, for all of these ligands, will either predict, all four of them sort of in this type of pose, or all four of them in this type of pose. So the question is, why does it pick this combined one? And so here, like the answer is super simple, which is why I like the example, it is basically that this one ligand, methylspiperone, simply just can't fit in the analogous pose here. So it's sort of just not an option to put methylspiperone in this pose. So basically this is kind of the model of the kind of the most similar pose to this one, and you'll see that there's a clash between this serine and methylspiperone. So yeah, this is why Combine seems to pick this pose for all of the ligands. And the second question of interest is, of course, was this a correct prediction? So it was a bit challenging to come up with mutagenesis experiments to test this because of the kind of pseudo-symmetric nature of the interaction here. But we did hypothesize that, if we compared pimazide and benperidol, that there was a much different interaction around this serine. So we thought that, okay, like pimazide is sort of, basically clashing with the serine in this pose, whereas benperidol is not. Whereas in the kind of the docking prediction, the ligands are basically the same in this region of the binding pocket. So yeah, so kind of like supporting this poses, we observed that for pimazide, if we kind of make S193 bigger, we observe a decrease in the affinity, whereas if we for benperidol, it sort of stays the same, or perhaps gets a little bit better affinity even. Yeah, so with that, I want to move on to this kind of second application of our method to virtual screening. And yeah, so I'm sure most of you are kind of familiar with this problem. So basically here, the problem is that you're given a compound library and you want to identify which of these molecules might bind to the target with high affinity. And so here for our method, the inputs of the model are going to be the same as the combined method. So we're going to input the structure of the protein and a small set of known binders. And so our method is going to, this method, which we call combined VS, kind of proceeds in a few phases. So in the first phase, we simply just use combined to predict poses for our known binders. So at the end of this phase, we end up with just a set of poses for our three known binders. And then in the second pose, in the second phase, what we're going to do is we're going to calculate the combined score in the same way that we did for pose prediction, except now we're going to hold the poses for our known binders fixed and just compute the contribution of each of the libraries, each of the molecules from the library to the combined score. So for instance, for this first ligand, if we get our docking score is -9, and sort of this whole, like the negative log ratio of this ligand's similarity to these three sums up to -0.9. And then we'll simply end up with a combined score of negative 9.9. And so, like, interestingly here, you can sort of get ligands that have good combined scores, sort of either by having very good docking scores or high pose similarities. So here I'm showing a case where basically this ligand is forming the same key hydrogen bond as these ones. So it has a higher pose similarity than the first one. So despite it having a somewhat lower docking score, it's gonna, sorry, a somewhat worse docking score, it's gonna have a more favorable combined score. Oh yeah, I should mention here more negative is better. We're thinking about them as energies here. Right. So then using this, the final phase is simply to rank the ligands by their combined score. So to just look at this particular example, we can think of just right. So if we start out with a library of 2,400 molecules and we pick out 100, we can ask simply in this 100 how many binders do we get? And so random is very low. For standard docking, we get around 6. And then for this example, for combined VS, we get closer to 13. And so in the first part of the talk for binding post prediction, per ligand docking was the only reasonable benchmark. But here there's other things you can do. For instance, you can use sort of a ligand-based method. So here, this is assessing the chemical similarity of each of the ligands in the library to the known binders. And moreover, you can also take what I guess I'm calling a kind of an additive combination of the chemical similarity and the docking. So basically a case where instead of you sort of using the ligand information and the docking information kind of together, like as done in combined VS, you simply take the chemical similarity score and the per ligand docking score and combine them. So right, so you kind of have a two parallel trunks, and then you add them together at the end. Right. So yeah, so I should mention, so now I'm going to share some kind of aggregate results. So here I'm going to look at we're going to look at the enrichment factor, and the enrichment factor is basically the ratio of how many binders each method picks out over the random baseline. And so here I looked at 102 targets in the DUDE benchmark set. And so yeah, to get back to Jonathan's question from earlier, so in these benchmarks, we require that all of the ligands in the test set, so in the compound library, have a Tanimoto coefficient of under, I think it was 0.3, but it might be 0.25. I don't quite remember. So to all of the known binders. So here all of the molecules, yeah, so all of the ligands that we're testing on are quite different from the ligands that we're assuming that we know. So here we get about a 50% improvement when we get up to 6 or 11 known binders. And yeah, actually, so, and then kind of by construction, like by when we put in this constraint that the ligands need to be, sorry, that the library needs to be much different than our known binders, basically we find that sort of like standard chemical similarity methods can't perform well here. So they perform worse than standard docking on this benchmark set. And yeah, so interestingly, even this sort of combination of per ligand docking and chemical similarity kind of underperforms combined VS. Yeah. Yeah. So with that, I just to wrap up, I think I think the key takeaway is that we can really, it seems like there's an opportunity to use structure-based docking and ligand-based modeling sort of more closely. And like by doing so, it seems like you can get sort of like some kind of super additive improvements. So like, in particular, it seems like for structure-based modeling, you get a really strong starting point because it can work well with no target-specific information. But importantly, it also sort of boosts the performance of the ligand-based modeling by allowing the ligands to be represented by their interactions, which seems to be kind of a, some space where even chemically diverse ligands can be meaningfully compared and knowledge can be transferred. And then from the other side, the ligand-based modeling, I think it's fair to say that it's effectively solving an easier problem, one of kind of pattern recognition versus kind of this like physical predictions. So we can often get improved accuracy. But in addition, like interestingly, you can also, this information can improve the improve the quality of the structural models that you use in structure-based modeling. So yeah, I think there's, I hope that there'll be a lot more work in this direction, like in coming years. And I think it's a really cool way to sort of like boost the performance of machine learning with small data. So yeah, I genuinely hope that there'll be far better methods than the ones I'm presenting today soon. And yeah, and just in conclusion, I want to thank my lab members, so especially Julia Belk and Scott Hollingsworth, who led the project with me. And then also just a whole bunch of other people in our group who supported us. And then also, of course, Nico and Mary from the Sunahara group, who helped us with the perspective predictions at the D2 dopamine receptor. Yeah, so, and thanks all for listening. I'm happy to take any questions.
Great presentation, Joe. Thank you so much for sharing this work with us. If you have any question, feel free to raise your hand, but I know there's already a few questions in the chat, so
great.
You might want to start with that.
Yeah, so when computing the, I see. That is a good question. I should have a better memory for this. It could be either 1, 5, or 10. I'm really sorry. I would have to look it up in the paper. You can, it's included in our paper. It's titled Leveraging Non-Structural Data to Predict the Structures and Affinities of Protein Ligand Complexes. Sorry about that. Yeah, Jonathan.
Yeah, I'll try to limit the number of questions because I think this stuff is really fantastic, and I have tons of them. Maybe I can ask some of these privately, but one thing I'm really curious about is sort of the per target enrichment that you're getting. I just think, for example, for like kinases, I could draw. I'm not a chemist. I could draw a kinase inhibitor that is 0.5 or plus Tanimoto distance from known binders. Mm-hmm. But some of the more challenging targets, I can imagine this having a very, very hard time matching them. So was there some metric or even qualitative assessment for the challengingness of these targets, and did some of them dominate this enrichment factor, or was this very much across the board?
Yeah, that's a good question. So right, I'm forgetting the exact fraction of targets for which we observed an improvement. So actually, one thing I should note, in terms of just when comparing combined VS to just the per ligand docking, here it was not quite a strict improvement, but it was close. When comparing to the per ligand docking plus chemical similarity, here there was a little bit, it was a little bit more like for some targets, one was better than the other. I think this was largely coming from the fact that so since combined VS is using the per ligand docking score, like there's a reasonable correlation. So it tends to, like, it's easy for it to kind of do the same or better in this regard. But yeah, to get back to your question about sort of the relative challengingness of different targets. Yeah, here we didn't report, we didn't sort of look at the performance like broken down into different target classes, or frankly really think about like if any of the targets are specifically kind of fundamentally harder than the others in an intuitive sense. So yeah, sorry, unfortunately, I think the answer is no. We didn't look into that.
Which is perfectly reasonable. Just curious.
Yeah. And I see a question in the chat. Could you spend more time on how to calculate the score? Yeah, of course. So the yeah, to go into this. So for the inputs to the score is going to be poses for a set of ligands. So one pose per ligand. And so this first component of the score is simply going to be the sum of the physics-based docking scores. One thing that I'm realizing that I am missing here is depending on which docking engine you use, it might be that you have to add some constant here, basically to fit it such that it's in kilocal per mole. So the glide score is calibrated in kilocal per mole. So there we just left it as is. But otherwise it might be that you need to fit a constant. So then the second part, the idea, so here we're going to do a sum over all of the ligand pairs. So we're going to have n squared terms going in here. And then for each ligand pair, we're going to sum over each of the interaction types. So that was each of these four different terms. And then the individual term is going to be the log ratio of the frequency of the observed interaction similarity for that pose pair in the correct poses divided by the frequency of this observed similarity in all of the poses. And importantly, so this is the frequency in sort of the training set. So not the not just looking at the target specific data. So basically, like the way we do it is we compute these distributions before we even know what our target of interest is. And then so here, like when computing this green part, we simply are just looking up, okay, you have a similarity of 0.75 for this one. So you get this frequency term. Yeah, I hope that was more clear, but I'm of course happy to take more questions on this. This is kind of the core. So yeah.
So on this particular slide, the second term is basically computed use kind of, I think is more like a correction term of the binding of the docking score, right? And what like the way it's being computed is by using the training set of 30 protein and it's in 5,000 ligand, if I'm remember correctly, right?
Yeah, so I think there's about 500 ligands, but yeah, have several thousand pairs. Yeah.
Okay, cool. So I was wondering if you have kind of in terms of, because there's certain family of protein that are covered in the training set. I was wondering if you have kind of taken to study how well combined does, if like maybe you get away from the sort of the family of protein that had been seen in this particular training set.
Yeah, that's a great question. So yeah, honestly, we didn't, so we of course withheld the data from the target of interest when we were making our predictions, but we didn't exclude information from neighboring proteins. We did just look into like in our paper we use like the beta 2 as like our kind of our well like our main example, and there we did look on like if we just got rid of all of the information from other GPCRs, how well does the model perform, and actually it performed about the same. One thing is just that since this scoring function was relatively simple, we frankly weren't that worried about overfitting, just because like the kind of the contribution of any one protein to the scoring function was pretty minimal.
Okay, I see. Um, did you kind of compare like this kind of approach to people using interaction fingerprints?
Yeah, so that's interesting. Like in some sense, you could think like I think like fundamentally like our method is like using like the interaction. Oh, it actually, sorry, let me uh, are you thinking of cases where you sort of learn what I'll call like a generic scoring function, so one that you train on diverse data, and you learn some function mapping interaction fingerprints to whether the pose is correct or incorrect, or are you thinking of cases where you sort of perhaps assume that you know the interaction fingerprint for another ligand at the target of interest, and you're using that information?
I was thinking more about the second case, but I think the
Mhm.
first one is also particularly interesting. So you can comment
Yeah,
on both.
sure. So the for the second case, so two things. So one is we're focused on the case where we don't know the pose for any of the ligands. So yeah, there are a variety of methods that use known binding poses to predict additional ones. So here you could think of like our method as sort of extending this sort of method to cases where you don't know the poses for any ligand. So yeah, in some sense, I don't know if it's necessarily that we're kind of competing with these methods, because we kind of are one of these methods. Um, and then in the former case, no, we did not consider. Basically, we just considered glide as like kind of our stand-in for all physics-based or other kind of generic docking methods. Yeah, yeah. Um, uh,
Cool.
yeah,
Thank you.
Jonathan.
Yeah, I mean, this interaction fingerprint stuff is really interesting. There's a couple things I'm curious if you looked at that do something somewhat similar, but at the end of the day, still really are highly dependent on that docking score.
Mhm,
There's things like constrained docking, right, where you can say
mhm,
that certain interactions must be there. I think what you do is really great, which is you're looking at sort of conserved interactions across, similar ligands or diverse ligands.
mhm,
Um, the other thing is that there are some docking methods where you'll basically do like a three-dimensional pharmacophore shape
mhm,
match to,
mhm,
and then a score based off of that. But one thing I'm very curious about is I've seen some things come out of, for example, like RNA folding, or some of the protein folding stuff where they are developing these relatively low data regime machine learning models using things like equivariant nets, and then developing a score on that. And
mhm,
basically, did Rosetta Fold get it right or something like that? There's
mhm.
the Aries paper, I think, which was really cool. And I'm just curious if you've looked into something like that, or just have thoughts about how to use things like that might be a little less dependent on the interactions, but still using that structural information.
Yeah, I think coming up with, yeah, like better similarity metrics, yeah, perhaps based on like these equivariant neural nets, I think would be super cool. And I think it would be, um, yeah, I think like I think that would be an exciting area for future work. Like, yeah, one thing that I think, yeah, so there's two I'm thinking, yeah, so you could either use that to learn a similarity metric and then use the same framework to sort of transfer it into like some energy term, or you could just try to learn this outright. The latter is actually probably more sensical, realizing sensible. Yeah, I think, yeah, I think this would be a super cool area for future work. Yeah, and I think it should be possible. Yeah, it would just be a matter of setting up enough data to be able to learn these sorts of things. I suspect that you'd have trouble getting the same type of low data performance that my lab mates were able to get on the Aries paper, just because, you know, like RNA, like it has a limited set of components, right? So you at least see all of the components even on a small data set. I would worry that for small molecules, if you had a relatively small data set, you know, you might just never see some chemical group. So yeah, you'd probably have to be creative to get small data performance.